Hi, I'm Phil Velicities from the University of Michigan, and today we'll be talking about EEG voltage and power scales. And of note, the scales in this presentation are for illustration purposes only, and they're not completely accurate. So we'll just start with some basic electrophysiologic definitions as a review. So really, voltage is the potential for current flow from one place to another. So in other words, voltage doesn't describe the actual flow of ionized particles from one place to another, but rather voltage describes the pressure that pushes electricity through a conductor. The units of voltage are volts, and typically the order of magnitude with which we measure those with the EEG is relatively small. It's in the microvolt range. So how do we measure the voltage deflections with the EEG? So typically, EEG signals that we measure on the scalp are thought to arise from postsynaptic activation of cortical pyramidal neurons. So essentially what we think is happening is that we have axonal input from other cortical neurons or thalamic neurons that are activating apical dendrites of cortical pyramidal neurons. Now when these dendrites are activated, charged particles are flowing into the dendrites and then through the cell into the cell body, creating a current. And in doing so, there's a voltage potential that's created in the extracellular space. And that extracellular postsynaptic voltage potential is what we believe to be measuring with our EEG recordings. So if you get a large number of neurons that are oriented along the same axis, that are also perpendicular to an EEG scalp electrode, and those large number of neurons are all activated at the same time, this can act as a single dipole that we record with the EEG electrodes. And so we can see with a lot of these neurons that are activated at the same time, we get one large dipole activation that's reflected in our voltage deflection analysis here. So when large groups of neurons are activated at the same time with a certain frequency, that's sort of what gives our characteristic EEG waveform appearance that we're used to seeing. In this picture, this happens to be a 9 hertz frequency waveform with time on the x-axis and our voltage amplitude measurement on the y-axis. So changing the voltage on our EEG monitoring devices really can produce markedly different waveforms based on the chosen voltage scale. So we showed a moment ago our 10 microvolt scale here in the middle, and you can see that if you were to then increase the scale by an order of magnitude to 100, it gives off almost an isoelectric appearance. If you were to decrease the scale to 1 microvolt, you can see that the amplitude deflections that are recorded are much larger. So as an example, in this EEG recording, we have a fictional scale set to 10 microvolts. And again, this gives kind of our classic EEG waveform appearance that many of us are probably used to seeing. If we increase the amplitude to 100 microvolts, again, it gives off that sort of isoelectric like appearance. And if we were to decrease the amplitude to 1 microvolt, the voltage amplitude deflections recorded are much larger. So really, it's really important to appropriately choose the right voltage scale to give the optimal waveform resolution with which you're working on your EEG monitoring device. And this is sort of all three of those waveforms juxtaposed among each other. So for most patients and most of our scenarios, typically that's in the 5 to 10 microvolt range for most patients.